Welcome to the second day. And maybe let me first briefly recall what we have done yesterday, and we'll just give you a quick reflection on the memory of the definition of and properties of entropy. So recall that we define the Shannon entropy of a random variable x as the sum of negative p of capital X equals x times log of that. Then we talk about the Shannon encoding theorem. That's the motivation. And basically, the entropy tells you how much information the random variable contains measured in bits. So we can also define the conditional entropy x given y, which is the entropy of xy minus the entropy of y. It's like the increment if you want to know both x and y, but you already know y. That's the increment amount of entropy. And we talk about another equivalent definition, which is saying that you take the expectation over all outcomes of y and look at the entropy of x condition y equals y. And we also talk about some inequalities about entropies. The first one is the non-negativity, saying that any entropy term you see, even the condition one, are non-negative. And we also have the upper bound. This is upper bounded by the log of the size of the support. And this holds if and only if x is uniform. We also talk about some entropy calculation, like you can drop condition and also subadditivity and so on. So first thing is the subadditivity, h of xy is always less than or equal to h of x plus h of y. We also talk about dropping conditioning, which is kind of equivalent to the subadditivity. If you recall the definition of the conditional entropy, you can write the previous inequality in this way. So basically, these two says that no matter what, like suppose you already know y, you want to use some more bits to encode the information of x, you can just ignore all the parts about y and just encode x. So the conditional entropy is always upper bounded by the entropy itself, and these two equality holds if and only if x and y are independent. And we also talk about several situations about adding some information from deterministic functions. So let me just briefly list all the equalities and inequalities we have covered. So here we're also always assuming f is a deterministic function. Then we have this entropy is the same as the entropy of x condition y, so you get this deterministic function for free. And this is also the same as x condition y and f of y. And we also talk about some inequalities related to f. So the amount of information when x is composed into a deterministic function is always less than or equal to the amount of x itself carrying. So you have this inequality, and similar, you can compose the deterministic function in the y part, so you get this inequality. And in the last part, we talk about some combinatoric applications about like bitwise information. And we also use that idea to show like a brief outline of the proof of the union closed conjecture by Gilmer. So these are the topics we kind of covered yesterday. And today I would like to tell you something about graph homomorphisms. So maybe let me start with the definition of graph homomorphism. So I'm assuming everyone knows what is a graph, okay? So a graph homomorphism. So let's say we fix two graphs H and G. Then the collection of homomorphisms we denoted by capital H of capital hom. would be the collection of all the homomorphisms. So a homomorphism from H to G is basically just a function from the vertex set H to the vertex set of G, such that it preserves all the edges, namely f of uv, f of u, f of v is always an edge for all uv. That is an edge in H. So for these kind of functions, we call them a homomorphism between from H to G. And we use this notation HG to denote the collection of all possible homomorphisms from H to G. And since we care about counting, we'll use the lowercase hom to denote the number of homomorphisms. And sometimes we want to understand the density of the homomorphism. So imagine you have a complete graph, then the homomorphism in the complete graph from the homomorphism of a triangle in the complete graph is almost 4. Like you pick a random map, like with probability almost 1, you get a triangle. Like, so I'm saying like if you have a complete graph, then you pick any 3 vertices randomly. If none of these 3 vertices are the same, then you get a triangle automatically. So with probability 1 minus 01, you get a triangle. So you kind of want to say the density of that, the probability you hit a triangle is really high. So we define the notion of homomorphism density, basically just taking this number normalized by all the possible mapping from VH to VG. So the density of H to G is defined to be the hom from H to G normalized by all the number of possible mappings. So this is Vg to the power Vh. So this is the hom density. Okay, and there's one famous conjecture I would like to talk about today by Sidorenko, conjecturing something about the relation between the density of an arbitrary graph versus the density of an edge. So maybe let me start with the definition and tell you why it is defined in this way. So let's say a graph H is Sidorenko. If the homomorphism density of H inside any graph G is always lower bounded by the homomorphism density of an edge, which is K2, inside the graph G to the power E of H. So the power is the number of edges in H. If this holds for any target graph G, then we say that the graph H is Sidorenko. Does that make sense? And so let me give you a few remarks and tell you why it is defined in this way. So the first thing is that you might wonder why it is this exponent here, why you are you are raising the power to the number of edges. So if you consider graph GMP, and you compute so let's take G equals GMP. Although GMP is not an actual graph, but you can think of that as a graph. And you can think about the expected number or like expected density of H inside this GMP, the additionally random graph. So the expected number of the homomorphism density will be roughly P to the E of H. Because like if you pick randomly V of H many vertices, you know that each edge will have probability P to be connected, and there are E to the H many edges, so the density of that, the probability of like those vertices actually give you a copy of H, like a homomorphism of H, will be exactly this probability here. On the other hand, you can compute the expectation of a K2 in G. And basically, this is just P. So the Sidorenko conjecture, or like the Sidorenko property, basically says that the homomorphism density of H is lower bounded by a random graph. Like when the target graph is a random graph, that's the worst case you could have. Okay, and another thing is that if H is not bipartite, then H is not Sidorenko. And I guess this is not hard to see by just taking G to be a bipartite graph. Or you could simply take G to be just an edge. Because if H is not bipartite, there's no homomorphism from G to an edge, right? So the left-hand side of inequality will be 0, but the right-hand side is non-zero. So you could never expect anything if H is not bipartite. So there is a famous conjecture by Sidorenko saying that this is the only barrier. So he conjectured that every bipartite graph is Sidorenko. Okay, and although the conjecture is not solved fully, but there are many progress proving many families of graphs that are Sidorenko. And today I'm going to show you how to use the entropy method to prove like some of the graphs are Sidorenko and give you an idea like how do these proofs work. So maybe let me start with the easiest case, or the second easiest case. Like the easiest one is that H is K2, which is obvious. So let me start with the second easiest case, P2. So you have a path of length 2 with 3 vertices. And this is Sidorenko. So I'm going to first give you a proof without using entropy and let you feel like, and then tell you how to prove it with entropy. So since we care about the homomorphism density from a P2 to a graph, we might want to first compute the number of homomorphisms from P2 to a graph. And luckily, we can compute this explicitly using the degree sequences, right? Because if I fix the middle vertex here, I'm just picking 2 neighbors of that, and that'll give me a copy of homomorphism. That'll give me one homomorphism from P2 to G. So this is exactly the sum of some notations. The sum of all vertices in G, summing the degree squared. And we also know that we want to relate this one to the edge density. So we also want to compute the number of edges in G. And it is also given by the degree sequence. but this time you don't square it. So you just take one vertex and look at all the neighbors. That will give you a homomorphism from K2 to G. And by the way, so this will be 2m if m is the number of edges in G. So when we're talking about homomorphism copies, we always care about the automorphisms. We count each different automorphism many times. So for each edge, there are two orientations, so each edge is counted twice. So this is the number of homomorphisms in G. And I guess it's a middle school exercise to try to lower bound this one using this one, right? So you have sum of x squared, you want to lower bound by sum of x, so you use Cauchy-Schwarz. So you divide, that's okay. This. So you use Cauchy-Schwarz, viewing this n as a sum of many ones. This is thank you. And you divide by n on both sides, so you get put n. Okay, let me not do this. And remember, the density of P2 in G is the hom from P2 to G divided by the number of vertices in P2. So the number of vertices in G to the power number of vertices in P2. So that's n cubed. And the hom density from K2 to G is the hom from K2 to G divided by n squared. So if you really divide it by n cubed on both sides, sorry. Yeah, if you divide it by n to the fourth power on both sides, left hand side becomes this one, right hand side becomes this one squared. So is that clear? Okay, so let me tell you how to prove this with entropy. So the key idea of using all these entropy methods is that you want to sample something on the left-hand side of an inequality, uniformly at random, and try to do some entropic trick, like resampling random variables or computing the entropies. Any question there? Oh, okay. And then get some other combinatorial objects, like get some more random variables and upper bound the entropy of those random variables by uniform bound. So here, I guess the left-hand side, what is in the left-hand side? Let me write down. Squared, and here I want n. So this is the inequality we want, right? This is the goal, and let's forget about all the degree sequences, but you can rewrite the final inequality about P2 being Sidorenko, write that in terms of just the homomorphism, like not talking about density anymore, then this will be the equality you want. So I want to sample something appear in the right-hand side. That means I want to take a uniformly random edge. So I'm slightly abuse of notation here. Here, x and y is an ordered tuple, but usually the convention of edge set of G is unordered, but you know what I mean. So I'm taking this uniformly at random. And in particular, you have this symmetricity between xy and yx. That will not be super important here, but that will be kind of useful in our later purpose. So you should always remember when I talk about sampling an edge from a graph uniformly at random, it also has symmetricity between all the vertices in that edge. Okay, so let me start the proof. So now x and y, so the picture you should have in mind is that you now get two vertices x and y, and that will correspond to an edge in G, a random edge in G. And your goal is to find me a P2 and compute the entropy and upper bound that by the homomorphism number of P2. So what you can do is to fix one vertex. Which one? Fix, okay. So let's say I want to fix this y and do a conditional resample of x. So if I condition on the very random variable y, resample x, then I'll get another vertex, right? And since I'm doing conditional resample, this vertex should connect with this y as well. So condition on y, resample x, conditionally independently. And let's say we get z. Well, let's call this vertex z. So now we get a P2. And you can upper bound the entropy of these three guys, these three vertices, by the number of homomorphisms of P2 in G, right? Because that's a uniform bound. So on one hand, you know that the entropy of x, y, z is upper bounded by log of the hom of P2 in G. On the other hand, you want to connect this term with the entropy of just x and y, because I forgot to say, the reason we sample this is that the entropy of x and y is exactly the log of the hom of K2 in G. And remember, we want to connect this value versus this value. We want to show that this is roughly the square of this plus this log n term. So we want to express the entropy of this one in terms of the entropy of x and y. So I want to try to throw away try to remove the variable z, right? All the entropies related to z in terms of x and y. So the first thing I can do is to do chain rule. So this is exactly chain rule, right? But remember the way we sample z, we condition on y, sample an independent copy of x. So once we conditioned on y, there's nothing to do with x, right? So this is the same as h of z condition y. So here I'm trying to do it as slow as possible, and later you'll see me speeding up, doing these entropy calculations faster and faster. So I want to make sure everyone are comfortable with this calculation for the first time. So since x is independent, x and z are conditional independent from y, I can drop this x. And since y is a independent, it's a resample copy of x given y. So this is the same as the entropy of x given y. Is that okay? So now we rewrite, okay, let me also recover this term. So now we successfully rewrite this entropy in terms of the entropy of x and y with some conditional terms. And remember, our goal is to connect this with the edge density. So I might want to decompose this one, rewrite this one as using the definition of conditional entropy to write this as h of xy minus h of y. So you get two copies of h of xy minus a copy of h of y. Okay, so what does this show us? So I guess it shows us that twice of the entropy of x and y is less than or equal to h of xyz plus h of y. Right? And this is a P2, this is a vertex. So the inequality you should have in mind is exactly this one. So this is a P2, this is an x. Sorry, this is a vertex, and this is a K2 on the left-hand side. And indeed, this is true by the uniform bound, since the left-hand side we are sampling uniformly at random. This is log twice log 2 of the hum of K2 in G. And on the other hand, the right-hand side, you use uniform bound for this item and this item here. This is a P2, this is a vertex. So this is the log of hum of P2. And this is a copy of N. So we prove the desired inequality. And I guess one lesson here is that all these calculations are isomorphic to these Cauchy-Schwarz inequality calculations here. And indeed, you'll see some much complicated entropic inequalities later. And morally speaking, more or less, you can prove them via Cauchy-Schwarz or generalized holder. But I feel like entropy is a better framework to play with these homomorphism density inequalities. Okay, are there any questions? Okay, so maybe let's do the next case. So since we talked about P1, which is just an edge, and P2, which is this graph, let's talk about P3. And indeed, P3 is also Sidorenko. And in your homework, you'll see that you'll be asked to prove that any trees are Sidorenko. By the way, have you got the homework sheet? Okay, so let's try to prove P3 is Sidorenko. So again, proving P3 is Sidorenko, we want to connect the number of P3, connect that with the number of edges, like lower bounded by the number of edges, or like number of homomorphisms of edges in G. So again, we want to sample an edge uniformly at random. That's the only thing we can do so far. So let's again take X and Y, that is in the edge set of G, uniformly at random. And so now the picture in your mind should be this one. You have an edge X and Y, and you can try to create a P3 out of, you want to create a P3 out of this pair X and Y. And the trick we learned there is that we can do conditional independent resample. And if you resample Y, so if you condition Y resample X, you get a Z that gives you a P2. So let me write it in the lazy convention. So by write this, I mean I'm sampling Y given, sorry, Z given Y, the same as using the low X given Y, and this should be conditionally independent. So if I do this, I get a vertex Z that gives me a P2. And you can extend this trick and get, like, make this path longer, right? So this time I can condition X, resample Y, and get a vertex W. So W given X is the same as Y given X, conditionally independent. So now you see a P3, the remaining task is to really compute the entropy of that and see if it is indeed lower bounded by the entropy of X and Y. So let's try to do the calculation. So you want to compute the entropy of the four vertices, W, X, Y, Z. And remember, since we started with X and Y, so let me put X and Y as the first term of our chain rule. And this is the second term, you get Z condition X and Y. And later, finally, you get W condition X, Y, Z. This is chain rule. And remember, our goal is similar as before. We want to express everything in terms of the entropy of X and Y. So we want to throw away, like, rewrite the entropy of Z and W in terms of X and Y. And here, this term is the same, right? So since I'm sampling Z conditionally independent from X, so yeah, sampling Z given Y conditionally independent from X, so you can cross out this term and replace this Z by X. So this term is the same as the entropy of X given Y. So this is the same as this part. And for this part, since I'm sampling W, like W will be independent from both Y and Z. There's nothing to do with Y and Z. So I can cross out this Y and Z. And W is only depending on X. And since we sample W having the same law as Y condition on X, so this is the same as the entropy of Y given X. So far, so good. Okay, so let's finish the calculation. Now we successfully write this entropy of a P3. So in your mind, you should always think these four variables as a P3. You write the entropy of a P3 in terms of the entropy of X and Y and X condition Y, Y condition X, and so on. So you could rewrite this one as the entropy of an edge. So this is 3 times of the entropy of xy minus entropy of x minus edge of y. Right? Because I'm just rewrite this term using chain rule, using the definition of conditional entropy, or you could call it chain rule, and rewrite this term as well. So you get these 3 terms. And this is indeed the inequality we want, right? Remember, we have 1 copy of P3. We want to lower bound by the edge density to the 3rd power. And after taking log, this is 3 times number of the log of edges. So this is kind of in a good shape. So it remains to just rearrange the inequality, rearrange all the terms. And YZ plus h of x plus h of y. And since we sample the left-hand side uniformly at random, this will give us 3 times the log of the hom density. And on the right-hand side, this is a P2. Sorry, this is a P3. And this is a vertex, this is a vertex. And if you take the exponential back and rearrange terms, you end up with this inequality. Divided by L squared. And you want to normalize, make it back to the homomorphism density. So there are 4 vertices here. You divide it by n to the 4, and you divide it by another n to the 4 here, becomes n to the 6. And this 6 with this 3, this is the n squared and cube outside. And this is the homomorphism density of an edge, homomorphism density of a P3, so that proves the Sidorenko for P3. Okay. Yes.
For this proof, how can we rewrite this entropy proof to a conjecture as well?
Yes, so for this one, good question. So
We fix
so you first fix x, so this is sum over v. You want to sum the degree of v and the number of p2 out of v. Right? You want to sum the number of p2 out of v.
Yes.
And you use Cauchy rods, you get degree square and wait, you get p square. That let me think about that. Yeah, I never tried it myself, but I mean, you could do that.
Yeah,
If you are interested, I can figure out how to write it later. But
Okay, thanks.
yes,
On top of all, why is the entropy of x right there smaller than or equal to the log to the number of moles per P to P, rather than just equal to?
which one?
H X Y Z.
You mean this proof?
So I think he is asking the step using the uniform bound.
This one?
Yeah.
And the reason is that XYZ might not be uniformly.
Yes, XYZ might not be uniform on all the P2s.
Oh,
It's just some probabilistic distribution.
Let me give you an example. So imagine you replace P2 by a large star, and there is a vertex that has many neighbors in G, and the other vertex have low degree. Then it will be, if you sample a uniform random star, it will be more likely to hit that vertex than the other, right? But here, the distribution of all the vertices X, Y, Z, in particular the middle vertex of that star, will still have the same distribution as the edge distribution we started with. So you won't see that high degree vertex that significantly. So the distribution will be different. And that's where the slackness come from. Let me erase the board and I'll have more questions. Okay, so here I told you how to do conditional independent resample, and every time I get a new D, you might wonder what if the graph is not a tree. So indeed, we can also do something more fancy. So let me show you C4 is Sidorenko. So now again, the proof always starts with the same sentence. We sample an edge uniformly at random for X and Y in E of G uniformly at random. And we want to try to start from this edge, do some resampling or conditional resampling to get a C4. So remember, a C4 looks like this. And now we only have an edge, which is X and Y. So you could try to first build an edge out of Y by using the first conditional resample trick. So you get Z. So Z is a RP of X given Y. Then if I condition both X and Z, and I flip this Y, that will give me a C4, right? So I can condition this X and Z, flip this Y, which should be for W. So I'm sampling W given XZ, the same as Y given XZ, condition independently. But here is one issue, like you're conditioning two different vertices, so the entropy term might be harder to calculate. So sometimes in some situation, you cannot just naively say that I want to condition on some of the set of my vertices and resample some of the other vertices. In this way, some of the entropy term you might not know how to control, but luckily in this case, we know how to compute the entropy term, and I'm going to show you how to do so. So again, we start from XYZW. This is the entropy of the C4 we want to compute. We want to lower bound it by the entropy related to X and Y. Again, we can do train rule, but this time I'm going to do it slightly slower. So usually we always do the train rule in the order, like in the reverse order we sample things. So we sample X, Y, Z, and then W. So I'm going to first compute the conditional entropy of W, condition all the others, and then compute the other terms as well. So I'm going to first break out the entropy of W condition X, Y, Z, and compute this term first. Okay, so how do we get this to W? We do it in this way. In particular, it has nothing to do with Y, so we can first throw away this Y. So this is edge of W given XZ. And again, since W given XZ is the same as Y given XZ, so this is the same as Y given XZ. And you can break this one, you can break this Y equals XZ, so Y condition XZ into entropy of XYZ minus the entropy of X and Z. So the issue here is that these two vertices XZ, in our picture, if you just look at X and Z themselves, there's no edge there. So you're expecting them to be two copies of vertices, and the only way you can do uniform bound applying to these two vertices is that you can only upper bound by n squared, the log of n squared, which is just two independent copy of vertices. But sometimes X and Z might be correlated because you know X and Z, in particular, you know there is a path of length 2 between X and Z. So sometimes this upper bound by n squared would not be tight. And in those situations, the way of sampling like this will be bad. That's what I mentioned, what I was saying. But luckily in this case, you can easily upper bound this term by n squared, that will be fine. So let's proceed with the calculation and we'll see what I mean. So now we rewrite this W condition XYZ as the difference between these two terms. So let's put it back. So the entropy of 4 terms is the same as twice of the entropy of XYZ minus the entropy of XZ. And we want to compute this term. So remember, entropy of XYZ is the same as the entropy of XY given Z. So XY plus the entropy of Z given XY. And all these calculations are the same as the P2 calculations, so I will just write it down. This is X given Y. Okay, so you combine all these, you get the entropy of X, Y, Z, W is the same as the entropy of 4 times h of xy minus 2 times h of y minus h of x and h of z. And so you can rearrange terms. You have 4h of xy is the same as h of xyzw. This is the C4 we want. Plus 2h of y, these are vertices that are fine. And h of xz. So you can upper bound this by everything the same, but you use some additivity here. And we know this is a C4, this is 2 vertices. These are vertex and vertex. So the left-hand side is 4 log of C4 in G. And the right-hand side is this one.
Oh, sorry, that should be edge density.
This one?
Left-hand side should be edge K2T.
Oh, thank you. It's K2. And this should be C4. So this copy, this copy, this copy, this copy, each of them give you the log n. So you get 4 log n. And if you really rearrange term and sort everything out, you get E of C4. So let me write it as a K2 in G divided by n squared. So research. less than or equal to the first power less than or equal to the sum of C4 in G divided by n to the 4. So here you have n to the 8 here. In the denominator, you have n to the 4, and they cancel become this n to the 4. So I'm just saying the power of n matrix on both sides. That's the only thing you need to check. And indeed, since all the number of random variables are the same, it will automatically hold. So it will really becomes a homomorphism density inequality.
When we do it more symmetrically by sampling XYZ, P2 uniformly random, perhaps uniformly random, and then conditional XZ resample the field, and then apply one more time the Sidorenko or XYZ to obtain results.
Right, but I mean, so basically you said the gap between the entropy of C4 versus the actual number of C4 is kind of upper bounded by the gap of number of P2 versus the actual P2, right? Yeah, and yeah, that's true, but I mean, in practice, we don't know how to control each of these terms. I guess you can say something about P2, but sometimes it's getting harder.
So what I'm saying is, there's a, if you do Sidorenko, you can cut along XZ,
Yes.
and then you can cut along Y to do 2 times Cauchy-Schwarz. If
Oh,
you do
you're-
Cauchy-Schwarz,
Right.
then can we do this 2 times in the entropy way? This will be more symmetry here.
I think that corresponds to this calculation, although this is not quite clear, but when you're doing this is a Cauchy-Schwarz fixing X and Z and
Or we
do versus Y. And you do another Cauchy-Schwarz here, fixing this Y and do the X and part.
maybe it's essentially the same.
Yeah,
Just
so-
minor difference. Okay.
That's the way I would like to remember how the Cauchy-Schwarz step work. It's like when you condition on something, the something will be under the sum of Cauchy-Schwarz. And the thing you are resampling will appear in the summation of the Cauchy-Schwarz.
And in Sidorenko's conjecture, we want to dominate single edge. We want to say a bipartite graph H dominates an edge in that way. And if we want to say a bipartite graph dominates another bipartite graph, do we start by sampling this smaller bipartite graph?
Yes. And one remark is that you will see, I guess tomorrow you will see how to use Sidorenko to prove, so how to use entropy and shears to prove generalized holder, and the connection between how you do these Cauchy-Schwarz versus how you play with entropy will be more clear. Okay, so we see P4 are Sidorenko, and in another exercises of your homework, P4 is indeed K22, and you can actually show that K as T for any complete bipartite graph are always Sidorenko. Okay, so the third thing I would like to talk about today about Sidorenko is that hypercubes are Sidorenko. So by
Is there a direct way to generalize these arguments showing that every PL or every CL, every C2L is the right?
yes, so first is that every tree is Sidorenko. You can that's a homework.
Yeah, I mean, I know that, but
So
I heard
here,
that.
PL is a trigger. And for C2L, you take a PL and you do this reflection. So you can still do this trick to condition these two vertices to get the other one. So give you C2L is also Sidorenko. Okay, so let me first define what is a hypercube in an abstract way. By abstract, I mean I'm abstract. 抽象. Okay, so I'm just drawing pictures. I'm not going to write down the formal definition of vertices and edges. So a hypercube basically you just take. So for Q0 is a vertex, Q1 is an edge, Q2 will be you take a Q1 and you take another copy of Q1 and connect the corresponding edges. Then Q3 We just take two copies of Q2. So this is a Q2, this is a Q2, and you connect the corresponding edges. So you get Qn. That'll be the hypercube graph. And these graphs are always Sidorenko. And I guess from the way I'm describing that, it kind of suggesting us that we want to sample these vertices in the way I just described. We want to kind of start from the previous cube and sample the next cube and do kind of induction to build a larger and larger hypercube and also compute, like control their entropy along the way. So let's get started. So again, the very first step, we sample xy in the edge of G uniformly at random. This will be always the same starting point. And let's call this x and y. Okay, let's call x. Let's say our Q0 is just the vertex x. And Q1 is edge xy. So how to build Q2? It's the C4, right? So I'm going to build Q2 in the same way.
There's also color change here. You know.
Oh, maybe. Sorry. Again, I'm fixing this x and y and extend that to z by doing this condition y resample x becomes z, in condition x z resample y becomes w. And indeed, I can build Qn in the same way. So let's say you have a Qn minus 1. You have a Qn minus 1. That is a cup. There are two copies of Qn minus 2 inside.
Minus one. Minus two. Okay.
Yeah, minus 2. So this is a Qn minus 1. That's why I'm saying.
Okay.
Yes. And this is a perfect match. And let's assume we sample, let's call this part A and this part B. Let's assume we can sample in the way that A and B are symmetric. So in particular, the distribution of A and B are the same as the distribution of B and A. So we want to always keep this property along the way when we are doing this resample. I did works. This is the Qn minus 1. So that's the inductive assumption we want to induct. So assuming we have a copy of Qn minus 1 such that these two parts are symmetric in their law, then we want to build the next Qn so that it also satisfies this property. And I guess it's quite clear that we could do the same trick as here. We have an A, a B. So I can do the condition resample, get a C, and then reflect that, get a D. So let's do that and check all the marginal distribution criterion. So I'm going to resample A, resample, let's call this blob C. This is also a perfect matching. So I'm going to resample C given B. Conditional independent B getting from resampling A given B. And then do the reflection trick. So I'm going to fix A and C resample B. So it's A and C resample B. And let's say we get D. So now the whole copy becomes a Qn. So this is a Qn. So what's the entropy? Okay, before computing entropy, let's first check in this way of resampling, all the marginal distribution agrees. So I still have this condition. I want to tell you which part will be my new A and which part will be my new B. And indeed, you can pick any part like this pair versus this pair is symmetric because of the way you condition resample. Like, you know, the marginal distribution of AB is the same as the marginal distribution of CB because you do this resample. And you also flip this one, so the marginal distribution of CB will be the same as the marginal distribution of CD. And here we are saying AB is the same as BA, so you do all the reflections. You also know CD is the same as BC, and you also know this CD pair is the same as AB pair because we just do this like this thing. Is that hand wavy clear enough? So Q1 also satisfy the condition. And you can keep sample these hypercubes. Okay, so it remains to compute all the entropy and show you that indeed Q1 is indeed Sidorenko. So let's try to compute it. Oh, no, h of Q1 is the same as h of ABC plus h of D given ABC. So ABCD are these four parts. And basically the calculation will be identical to the C4 calculation, but instead of XYZW, we have ABCD now. So maybe let's just do it kind of quickly. By the C4 calculation there, we know that this is lower bounded by 4H of AB minus 4H of A. So here so here in the C4 calculation, you know H of XYZW is the same as 4xy minus 2y minus 2h of xz. And you can use subadditivity to break this into h of x and h of z. And you know all the marginal distribution of y and x and z are the same. So I'm just gonna replace all of them by the entropy of x. So in here, I get lower bounded by 4 times h of AB minus 4 times h of A. So this is indeed the same calculation on both sides. Okay, so what does this tell us? What is h of AB? What is the pair AB? It's indeed Qn minus 1. And A itself is a copy of Qn minus 2. So this is indeed, let me write in this way. So you could do the telescope sum and cancel in these terms and do the recursion, reduce that to the entropy of Q1, which is an edge, versus the entropy of Q0, which is a vertex. So let me just write down all the details here. So for comedians, let me denote the decay to be okay, let me do it this way. So I'm going to define dk to be the homomorphism density we want, which means that I'm going to take the number of homomorphisms. This is like you should think of this even. You should think of this h of Qn as the log of number of homomorphisms. And if you want to get homomorphism densities, I need to subtract by n to the 2 to the k, right? Because 2 to the n is the number of vertices in Q1. So if I subtract by this, or after taking exponential divided by n to a 2 to the n, there are two different n's. I see why I wrote k on my note. And we also replace all of these by k. Okay. So n is the number of vertices in G, and k is the size, the dimension of a hypercube. So if I write this, I should think of this term as the homomorphism density, and indeed it is always upper bounded by the homomorphism density. And in particular, D1 is the entropy of Q1 minus 2 log n, which is indeed a homomorphism density, right? Because we pick this uniformly at random. So this is log of P of K2 in G. This is what we want. And D0 is 0 because D0 is not 0. D0 is negative because D0 is the entropy of Q0 minus log n. And Q0 is just a vertex, so this will be always less than or equal to 0. And we have the recursion, so you can rewrite this as a recursion that dk is greater than or equal to 4dk minus 1 minus 4dk minus 2. Right? So we want to do this telescope sum. So the next term, I should put 4dk minus 1 here, greater than 16dk minus 2 here, minus 16dk minus 3 here, so that this term will cancel with this term, right? I want to kill all the dk minus 1, dk minus 2 terms and so on, and leave only dk and d1, d0. So this term will cancel with this term, and this term will cancel with some part of this term, so the next term should be 12 times dk minus 2. And this will be 4 times, so it's 48 dk minus 3 minus 48.
Is that correct?
minus
This
4.
in dk there's a minus 2 to the k term. Is that correct?
This one?
Yeah. If you're plugging up there.
Oh, yeah. Sorry, I have it. I forgot to tell you that. So the number of vertices, so this is the 2 to k is the number of vertices, which is the number of random variables inside each tuple. You should think of this qk as a tuple with 2 to a k vertices. And the inequality is homogeneous, meaning that the number of random variables here, if you think of this as a tuple, is the same as the number of random variable on the right-hand side. And you can indeed check that. This is 2 to the k. On the left-hand side, you have 2 to the k variables. And here you have 4 times 2 to the k minus 1 variables, minus 4 times 2 to the k minus 2 variables. And indeed, this 2 to the k is the same as this 2 to the k I'm saying. And these two numbers are the same. Right? Because this minus this is 2 to the k minus 2 times 4 is 2 to the k.
Or I'm a bit confused by the 30 equality.
This one?
Yes, should that be equal? Because I believe that this AB should in a uniform distribution as 2k minus 1, but how about A? I mean, it's
so here I'm not saying they are uniformly distributed on all the outcomes of qk minus 1. I'm just saying I do this resample trick inductively and call each block. So I'm going to call this qn minus 2, and this qn minus 2, and this whole copy qn minus 1, and do the resample trick to call all these random variables I get qn. So I'm just building that recursively. So these are indeed tuples of random variables that I build.
Why is D0 not 0?
Which one?
The last one. Why isn't D0 not 0?
Because this might not be uniform. If you pick a uniform edge, the marginal distribution of a vertex might not be a uniform vertex. But if you're proving Sidorenko, there are some reductions saying it's fine to assume it's regular, so you could make this uniform. But in general, it will be less than or equal to 0. It will be it might not be uniform. Okay, so yes, I'm just trying to convince you. You should trust me if I do I minus I then or equal to I plus 1 to I plus 2 k minus I minus 1 minus I plus 1 to I plus 2 b k minus I minus 2. So this will be the intermediate equality. And if you trust me, all the middle term will cancel. So I'm just going to skip the steps and
Should we do a simpler way, like say define EK as DK minus 2 times DK minus 1. And then this automatic telescope thing.
really?
Yeah.
Okay. Anyways. Yeah, I didn't thought about this carefully. I just try to figure out a general pattern and do the telescope canceling term. But yeah, there might be a more clever way to do that. But whatever, the final term you will get is this is lower bounded by k times 2 to a k minus 1 d1 minus k minus 1 2 to the k d0. So this is negative. This is non-positive, so the whole thing doesn't hurt you. So you could kind of cover this term. So this is lower bounded by this, and this is the edge density. And this is the number of edges in dk. So this is upper bounded by the edge density from this line. So density.
Okay.
Okay, thank you. Yes. So this is upper bounded by the Hom density of QK. This is exactly the Hom density of an edge. So we prove Sidorenko. So far, so good.
Yeah, I have a question, very silly. So for Sidorenko, we don't need n to be sufficient long, n can be any constant.
Yes, n can be any constant, and indeed you can do either blow-up tricks or tensor power tricks, showing that if you have a small counterexample for n, that you can get a large counterexample.
Uh-huh.
Okay, so the next thing I would like to tell you is some homomorphism density inequalities of trees. So this is also proven by Sidorenko, and it's also about homomorphism density, but I think it's less well known. So it's a theorem by Sidorenko, saying that if T is a tree with k vertices, then the density of T inside any graph G is always upper bounded by a star of the same number of vertices. And you can also rewrite this as the Hom density, the number of homomorphism inequalities. So these two are the same because there is the same amount of vertices in both sides, in both T and the star. So basically, Sidorenko shows that among all the trees, of fixed number of vertices, the star is the one maximizes the number of homomorphisms. Okay, and the proof is quite clever. So I would like to talk about this. So the first claim.
Intuitively, is it because star is the most asymmetric one? So it has it's irrelevant.
Intuitively, it's like star has the most leaf. although that's kind of tautology, but you'll see like in this claim I'm going to tell you, you can always get a tree that has more leaves that has larger homomorphism density. So let's say you fix a graph T and you fix T and a graph G. So I'm saying fix. Then there exists a tree T prime. With more leaves. Such that the hom from T to G is less than or equal to the hom from T prime to G. I guess it's quite clear once we prove this claim, we can keep applying this claim and iterate, and the tree with the most leaf will be a star. So it's sufficient to show this claim, right? This claim implies the theorem directly. Okay. So as usual, if you want to prove some inequalities, we want to sample the left-hand side uniformly at random. So I'm going to sample xt, which is a tuple of vertices xv. So each xv is a random variable, and I'm going to tell you what is that. Here, the index v is labeled by the vertices in T. And indeed, this will be a random variable lies in the hom from T to G. So capital hom. Which means that I'm going to pick VT many vertices in my graph G, so that the copy of these VT vertices form a homomorphism of T. Does that make sense? So each xv will be a random variable, and it's supported on the vertex set of G. And the whole tuple as a tuple, that will give you a copy of homomorphisms from homomorphism copy of T inside G. I guess if you are confused, you should think of this xv as this xt as a tuple of say xyz when we are proving P2, and xyz are correspond to the three vertices in P2. So for each vertex, you have a random variable. Does that make sense? And we're going to play with these random variables. So I'm going to sample this uniformly at random, so that the entropy of xt is the log of the of T to G. Okay. So in the picture, you have this xt, where T is a tree. And let's pick two vertices V, U and V, one step away from a leaf. So I'm going to pick this to be U and this to be V. I'm picking two different vertices that both of them are one step away from some leaf. And I'm going to rewrite the entropy of xt using the chain rule. So this can, okay, let me first label all the leaves. So I'm going to call all the leaves out of U, call them xa, so x1 to xa. So these are lowercase x, and these are y1 to yb. So these are the leaves. And I'm going to remove first all the leaves from my T. So this is x1 to xa, y1 to yb. Plus all the entropies from the leaves. So this is entropy of x, x1 to xa, y1 to yb. So when I write this notation, I mean this is indeed a tuple, consists of x, x1, x, x2, x, x3, and xy1, xy2, xy3, all these random variables. And this condition on x of t tilde, so let me call this part t tilde. So this is the chain rule, and you can upper bound this by h of x t tilde. So this is x t tilde plus a times h of x sub x given x t tilde plus b copies of h of xy given x t tilde. So here I'm just using some additivity, breaking this x, x1, x, x2, x2, x, xa into all of these. And since you have symmetry here, all the x, x1, x, x2 have the same marginal distribution. So I'm going to call that x sub x. And this will be x sub y. So you have a copies of x sub x and b copies of x sub y. And you can further upper bound this by a copies of h of x sub x. But now I'm only going to condition xu. I'm going to throw away all the informations outside. And for the b part, or for the y part, I'm going to just get condition x sub v. And indeed, these two are equality. So since we are sampling this uniformly at random, you have some nice independence between random variables. And you can actually show that these two are equalities, but for our purpose, we only need an upper bound. Okay, so now we computed the entropy here. So the entropy is upper bounded by this. We might want to build a tree T prime that has more leaves out of these entropy. So you can think of these as a gadget we have, and we need to build a tree with more leaves using these gadgets. So there are two cases. So case one is that the entropy of the x part is larger. If this one is larger, I can upper bound all the y terms by the x terms. So this is that is upper bounded by entropy of x t tilde plus a plus b copies of h of xx given xu. But now you have this tree. This is t tilde. This is u, this is v. And indeed, you already have a vertices, x1 to x8. But so if you compute the entropy of x1 to x8, each of them give you one term of this. But now you have a plus b copies. So it kind of suggests us that I want to build b more leaves out of here using these gadgets. So I'm going to just sample x a plus I. Okay, I know the notations are horrible. I thought about it, but I don't have a good way to set up all the notations, but you get it. So I'm going to just condition xu resample all the x1. Condition u resample all the x1 to get my b other new copies of a plus I. To get b other new copies of the leaves that are identical to x1 in law. So for I equals 1 to b, so I'm going to sample b more leaves. And indeed, you can compute the new a plus 1 to x a plus b. So indeed, you can compute the entropy of the whole thing. x1 to x a plus 1 to x a plus b. So you can also compute the entropy of this one. So this is the same as the entropy of xt tilde plus the entropy of xx given the sum. Okay, here, like in the left-hand side, we only use upper bound, but here we indeed need the equality. This is because, you know, all the leaves here will be conditional independent given U, independent from the other part of the tree. Because so this tuple indeed has this entropy here, but this term is the same as this term. These two are the same. And you know this tuple is indeed a tuple that is supported on tree looks like this. So this whole tree will be my new T prime. So in this case, we found a tree with more leaves that has larger homomorphism density. So we'll finish the proof in case one. Is that clear? Okay, so what about case two? Case two is that this equality is flipped. But we can just move the leaves, instead of moving all the leaves from V to U, like do the other way around, moving all the leaves from U to V. So this finishes the proof. And we have proven the claim. So this is the theorem by Sidorenko. And I found this trick quite fun, quite interesting. Like, I mean, usually in most of the entropy inequality, we prove inequalities that just directly connecting inequalities by inequality. But this one we are splitting into two cases, comparing two like seemingly unrelated inequalities. And in either case, we do some combinatorial tricks to do resamples to get a different result. But in either way, we get a new tree and do the upper bound. Okay, so I have 5 minutes left. Let me maybe briefly tell you what's going on in tomorrow. So tomorrow we're going to talk about shears inequality, and we're going to look at several applications of shears inequality. So maybe let me first do a very simple version of shears inequality and prove that. And tomorrow you will see a full proof of a shears inequality. So the very simple case says that if you want to understand the entropy of the tuple of three random variables, it's always upper bounded by the tuple of xy, yz, and xz, but with some normalizing vectors. And the proof is indeed quite simple. It's like each of these entropy of tuples, you can break it into like conditional entropy using chain rule, and you just compare like the conditional entropy on both sides, and for some terms in the left-hand side you use drop conditioning, and you can do all the terms back into the form in the right-hand side. So I'm going to show you a simple proof. This is so we kind of want something looks like the right-hand side. So let me just write the left-hand side in terms of one term of the right-hand side plus some extra conditional entropy. And we can do this symmetrically. So this is h of yz given h of x given yz. And this is the same as h of xz plus h of y given xz. right? So I have 3 copies of h of xyz. I get h of xy, h of yz, and h of xz respectively. So now in the left-hand side here, in the shares inequality, I claim that I only need 2 copies here. So I want to use the extra term to kill one of the copy. But you know this term, so you have these 3 terms. And this term h of z given xy, we can upper bound it by just h of z, and maybe the next term h of x given yz, upper bounded by h of x given z. And in the last term, you just keep it the same, y given xz. It's the same as y given xz. So you add this with this with this. That's the chain rule, right? So you add them together, you get a copy of h of xyz. So you know 3 times of h of xyz is upper bounded by what we want, plus 1 copy of h of xyz. So that gives you a shares inequality. And tomorrow I'm going to state the full version of the shares inequality and prove some corollary, including the generalized holders, and probably you have heard of this application of triangle intersecting family and some other applications as well. That's it.